Hi, and welcome to QM Revision 6. Today we're going to be talking about wave-particle duality. So, when we talk about wave-particle duality, what we mean is there are lots of things that we normally think of as waves that have particle-like properties, and there are lots of things which we normally think as particles that have wave-like properties. So let's start with light. Newton thought that light was a particle. In fact, he thought it was made of little particles called corpuscles, which is a wonderful name. And he thought, imagine tiny little tennis balls just flying along, and that's what light is. And he had a really neat way of explaining refraction, which is he imagined that the corpuscles would just be flying along through the air, but then they'd suddenly get pulled towards denser media, like glass or water, and there'd be a force bending the particles into it. So it sort of get accelerated in as they got pulled in, and that's why they bent. And then when they left the glass on the other side, the glass would still be pulling them towards, and that would expend the bend the other way, because there's a force still towards the glass, so it would bend in and bend out. And thus, he thought, well, hey, I've got it. I've worked it all out and explained refraction. There is however a problem to this. Just pause the video, you can work out how you think in sort of 1800-ish they might have shown this was wrong. Well, if you think about Newton's solution, the particles are moving faster in the glass than they are in the air, because there's an acceleration force into the glass and deceleration force when you leave. So once they started to measure the speed of light in different media, specifically when they really started to measure it in water, what they found was it went much slower in glass and water than it did in air. Therefore, Newton's theory could not be correct. And the more wave theory of light, particularly advocated by a guy called Huygens, started to really come into the force. So we started to stop thinking about light being a particle and instead start thinking of it being more like a wave. This continued quite happily until about 1900, at which point, while we've talked about it a lot, so pause the video, what effect would tell us light acts more like a particle? The answer, of course, is the photoelectric effect. All the energy is arriving in these quantized lumps. There must be individual photons dumping off that energy, so therefore light must be a particle. And yet, it still acts like a wave sometimes. And this is our wave-particle duality. Light, sometimes a wave, sometimes a particle. Easy. But what about particles? Let us consider this textbook. This is surely just matter and never a wave, right? Well, it turns out that every piece of matter in the universe, every particle, is also a wave and has its own wavelength called the de Broglie wavelength. That is spelled like this for anyone keeping track at home. So the de Broglie wavelength of a particle tells you how wavy the particle is, and it's given by the wavelength is equal to h, which is just a constant, divided by the momentum. So as the momentum goes up, the wavelength goes down. It turns out if you whack the numbers in, you're not going to see things like me or a tennis ball ever act like a wave, because they'll have such pointlessly tiny wavelengths that you can never get them close enough to a gap such that they'll diffract. Because as we well know, diffraction only happens when the wavelength is similar to the gap that you're passing through. However, sometimes, especially with very small particles, we can observe this effect. If we get a beam of electrons and we pass them through a very small gap, if we get momentum such that their de Broglie wavelength is equal to the parting of the gap, they will actually diffract through the gap, and you will end up with your standard diffraction pattern. They won't fly straight through, but will instead act like a wave and spread out. So this particle, an electron, something we think as being very particulate, you can smack them at things, we can bounce them off things, they have all the properties of particles. If we get the speed right, and we get the size of gap correct, we'll suddenly start to act like waves. So waves sometimes act like particles, and particles sometimes act like waves. And this is our wave-particle duality. There's a question underneath. Have a good weekend. I'll see you next week.